So a couple words about myself. So I work as a researcher on JetBrains research, and I'm a postdoc in Victor Vifiadis group at Max Planck Institute for Software Systems. Also, I teach at Higher School of Economics. So my research interests are around programming languages and formal aspects of them. I'm mostly interested in weak memory concurrency and compilation correctness proofs. Also, I'm kind of interested in functional programming, and I'm not a software engineer. However, I see myself being proof engineer, so I still write a lot of code, but most of the code is in language called Coq. So Coq is some proof assistant which allows to write some complicated proofs which could be automatically checked by computer. So now let's get back to business, and the topic or the title of my talk is Programming Language Memory Models, Problems, Solutions, and Directions. So I think there is only one part of the title which might need some explanation, and it's memory model part. So under memory model, we use the term memory model to describe semantics of concurrent systems, which explain behaviors of concurrent systems like CPUs and programming languages with concurrency. And the question one might ask, isn't there like the memory model? In some sense, yes, there is memory model, introduced by Leslie Lamport in his paper, How to Make a Multiprocessor Computer That Correctly Executes Multiprocessor Programs. And this memory model is called sequential consistency. And in this memory model, all behaviors of concurrent program are described as sequential execution of some interleaving of program threads. So let's take a look at an example. So here we have some program which starts with some memory initialization. So here we have two shared locations x and y, and in the beginning of program they are initialized by zeros. And then program starts two threads. In each thread there are only two instructions. The first instruction is a write to either x or y, and then we read from the opposite location. So in sequential consistency, as I said, program behaviors are some sequential executions of interleaving of threads. So let's take a look at some interleaving of this program. So here we have a program, interleaving of the program where we first put the threads, instructions of the first thread and then instructions of the second thread. So if we assume that allocations are initialized by 0, then if we sequentially execute this program, we'll get result a equals 0, b equals 1. So this is one of the outcomes for this program allowed by sequential consistency. However, there are more interleavings of the threads. So one of them presented here. So here we start with executing the second thread and then the first one. If we execute this interleaving sequentially, we'll get result a equals 1, b equals 0. So there are more interleavings, actually 4 of them, all of them leading to result a equals 1, b equals 1. There are no other interleavings of the threads which preserve program order. So these 3 outcomes, there are only outcomes allowed by sequential consistency. So for example, result a equals 0, b equals 0 is disallowed by sequential consistency. It means that we can use this code as beginning of mutual exclusion algorithm. So for example, if we put these if statements in the end of each thread, since we know that a equals 0, b equals 0 result is impossible, we could prove that in sequential consistency there is no way for this for both critical sections to be executed. So if the program executes with the result a equals 0, b equals 1, then the critical section in the left thread is executed, but not in the right one. If a equals 1, b equals 0, then the second in the second thread critical section is executed, but in the first one not. And if we get result a equals 1, b equals 1, then none of the critical sections is executed. So there is no way to execute both critical sections. And actually, this is a very simplified form of Decker's log. However, if we write a program like this in C++ and execute on our laptops with x86 CPU, then we might observe that both critical sections are executed, meaning that this Decker log isn't correct. But why? So actually, there are two reasons. So first, we compile code, and compiler, for example, GCC, may reorder instructions. So if GCC knows that X and Y are distinguished locations, then in the left thread, it could reorder two independent accesses, write to X and reading from Y. So even if we forbid GCC from doing that, for example, by putting empty assembly instruction in between, then still, if we execute the code which is produced by compiler without any reorderings, x86 might execute this program in a way that both critical sections are executed. And the reason for that, because not only compiler is optimizing, but also CPU is optimizing. So x86 may buffer writes, and this is how we might observe result A equals 0, B equals 0. To fix that, in compilation, we need to insert some memory fence if we want to preserve correctness of Decker's log on x86. And after forbidding reordering done by GCC and inserting this assembly instruction, this memory fence, we guarantee that this code works properly on x86. So this outcome, A equals 0, B equals 0, which was possible for example on the previous slide before we put memory fence there, it's some behavior which cannot be observed on sequential consistent memory model. So such behaviors are called weak behaviors, and there are memory models allowing weak behaviors. They called weak memory models, and most of real concurrent systems have weak memory models. So, for example, all major CPU architectures, including x86, Power, ARM, and RISC-V, have weak memory models, and C++, Java have weak memory models. So there are two types of memory models, hardware ones and programming language ones, and there are different requirements for them. So from hardware memory model, we expect that it describes behavior of real CPU. So for example, if memory model disallows some outcome, it should not be possible to observe it on CPU, which corresponding CPU. Also, hardware memory models as formalisms which developers use for developing their programs has to save some room for future optimization. So for example, if we have some memory model now for x86 processor and Intel next year decides to make some more aggressive optimizations which break current memory model, it would be bad for us because we will have to rewrite or at least reconsider our programs. So if CPU manufacturer knows that it's going to modify CPU architectures, memory model should have some room for it. Also, hardware memory model should provide some reasonable guarantees for programming languages to for us to be able to compile to hardware memory models. Programming language memory models have different requirements. So first of all, if we want to support, if we want to have a compiler which does some optimizations for this language, these compiler optimizations should be allowed. So for example, as we saw in the example before, if GCC is able to reorder some instructions, then memory model of sequential consistency is not well suited for it. Also, programming language memory models should provide efficient compilation mappings to hardware and have some easy non-expert mode, because usually they are quite complicated, and it's nice if there is some way to restrict behaviors of programs if you write some nice programs. So let's so in the remainder of this talk, we'll focus on programming language memory models, requirements to them, and we'll consider existing memory models in the perspective of these requirements. So let's take a look at the requirements in more detail. So one of them, as I said, is soundness of compile optimizations. So for example, if we have the program which we already considered, and we want a compiler to be able to reorder instructions in the first thread, leading to the optimized version of the program there they reordered, then if some behavior is allowed for optimized program, it should also be allowed for the initial one. And the reason for that is because you have a memory model which says, okay, for this program you cannot get a equals 0, b equals 0, and then compiler does some optimization, and then you observe this behavior which was not allowed. This is a bad situation, right? So since memory models usually provide non-deterministic semantics to programs, usually we represent semantics of a program as a set of outcomes or some executions, and the set for optimized program should be included in the set for the original program. So here we use square brackets to denote semantics of program inside of them. Okay, the second criteria is efficient compilation to hardware. So suppose we want to support sequential consistency of the level of programming language, and we want to be able to compile to x86. So as we discussed before, for this program we'll have to insert fences. And this is the usual case. If you want to support sequential consistency, you have to insert some fences in compiled program to preserve it. So this compilation scheme is not fully efficient because we have to insert such fences. So for example, C++, this is not a solution for C++ where we want to have full control over performance and we want to be able to use all performance from hardware. Okay, and the third requirement for programming language memory models is having easy non-expert mode. So usually it has a form. If you have some nice program, then it has only nice behaviors. So in the setting of memory models, it usually means that if you have a program without data races, then you have only C behaviors. And more specifically, usually we define the notion of data races in terms of sequential consistency and say if there is no data races in sequential consistency, then there are only C behaviors. So this essentially allows for developers to know only C semantics if they can write nice programs. This guarantee is called data race freedom guarantee, and memory models try to provide it. So for example, here we have a program where first we read from location x and y. We, as always, assume that these locations are initialized by 0, and then we have control dependency to some write. So for this program, in sequential consistency, the only outcome we could get is a equals 0, b equals 0. And actually, in sequential consistency, there is no data race. So for nice memory model, we would expect that it would allow only outcome of a equals 0, b equals 0. However, it's not the case, for example, for C++ memory model. So it allows to get a equals 1, b equals 1 for this program. And I need to notice that there is no way to get this behavior in real life. So usually it's impossible for this program to get result a equals 1, b equals 1. However, the formal semantics of C++ allows to get it. So it's a well-known flaw in C++ memory model. And actually, this flaw has a name, and it's called out of thin air outcome or out of thin air values. So if we want to have data race freedom guarantee, we don't want to have out of thin air. Now let's take a look at the most well-known memory models in the context of in the context of the requirements we just described. So first we'll start with sequential consistency, and actually it's okay in terms of compiler optimizations, so it allows some of them. Let's take a look. So first of all, sequential consistency allows trace preserving transformation. This is some transformations which don't modify memory accesses. So for example, if you do loop unrolling, it's some trace preserving transformation. However, as we saw in the Decker's lock example, sequential consistency doesn't allow reordering of memory accesses. But for example, it allows redundant read after read elimination. So this is an optimization. If you have in the program two reads from the same location, then essentially you could remove the second one and just use the value you get from the first one. Okay. So as I said, there are some optimizations, and actually there are quite a lot of them which are supported by sequential consistency, but there are some which are not. And then the question is, what would be if we just turn off optimizations used by modern compilers which break sequential consistency? So actually there is a work which tested this idea, and they get average slowdown of 34% for some modified version of LLVM, where they just turned off optimizations breaking sequential consistency. However, if they fixed these optimizations, they even get a much smaller slowdown of 5.5%. And now one might ask if, okay, 5.5% is not that much of slowdown. So maybe it's okay if we force to have SC semantics for our language with just paying this 5.5% slowdown. However, it's not that. It's not enough. And the reason for that, we by restricting or fixing compiler optimizations to preserve SC, we don't get end-to-end sequential consistency. We just fix it for compiler. However, hardware is still allowed to get weak behaviors for our programs. Also, the drawback of this approach is that you have to modify existing compilers if you want to get some reasonable slowdown. Okay. Now let's get back to our table and take a look at Java memory model. So actually, the interesting thing is that Java memory model has, in my opinion, even worse situation than sequential consistency in terms of allowing compiler optimizations. And why is that? So if we take a look at the table, we'll see that, okay, there are some optimizations which are not allowed by sequential consistency, but allowed by Java memory model, like reordering of normal memory access. But there are some optimizations, like redundant read after read elimination, which are allowed by sequential consistency, but not by Java memory model. And actually, redundant read after read elimination is kind of a bad example in the sense that for Java memory model, because it used to be used by hotspot implementation of JVM, although this optimization is broken, so is not allowed by Java memory model. So it means that hotspot at some point was broken regarding Java memory model. So the fact that hotspot was doing this optimization means that it's a reasonable optimization which is needed for performance. However, it wasn't. It is not supported by Java memory model. Okay. Speaking about compiler optimizations and common memory model, C++ has quite good situation in this regard. So it allows quite a lot of compiler optimizations. Okay, now let's get to the second row. second column, and discuss efficiency of compilation to hardware. So if we want to support sequential consistency, it's kind of expensive. So let's take a look and see why. So actually, there is some work which tried to do something like that, exploiting Java memory model DRF guarantee. So again, data race freedom guarantee is essentially says that if you have no data races, then you have a C semantics. In case of Java memory model, it also means if all shared locations in your program are volatile, it means that you have a C semantics. So volatile is a special flag which allows you to put to a location, and then Java memory model provides some specific guarantees for these accesses. So they are usually compiled with some fences to hardware, and this is how C semantics is preserved for them. So the idea used by authors was to make all accesses all shared accesses in JVM to be volatile, and that would lead to end-to-end sequential consistency. So they tested this approach on x86 architecture and 2 different ARM servers on 2 sets of benchmarks. So first they used this Da Capo benchmark, which includes some big Java projects like Gton, Tomcat, and Eclipse. And also they tested this volatile Java memory Java virtual machine on Apache Spark benchmarks. So here they are denoted by Spark perf. So for x86, they got average slowdown of 28% for Da Capo benchmark and 79% for Spark, and maximum slowdown of 81% for Da Capo and 164% for Spark. So one might say that it's not that much if we preserve end-to-end SC. However, if we see results for ARM, they are more disappointing. So average slowdown for Da Capo benchmark is 57% for first ARM server and 85% for Spark performance tests. And actually, maximum slowdown for Spark performance tests was kind of high. It was more than 500%. For other CPU, they got quite similar results. So if you could trade up to 164% on x86 performance, then sure you could have end-to-end sequential consistency. But on ARM, it's much more expensive because ARM has a weaker semantics than x86, so it allows more reorderings at the level of hardware. It's kind of expensive to implement sequential consistency on modern hardware. So Java memory model and C++ actually have quite a good situation. So they allow for optimal compilation to hardware. Although there is some interesting bit. Is that currently Java memory model has it compiled. Hotspot implementation for IBM Power compiles volatile accesses actually even more optimal, which is when it's allowed by Java memory model. So actually, Java memory model requires some fences where hotspot implementation for IBM Power doesn't put them, and this is some flaw in hotspot. I'm not going to talk about this in the main talk, although I'll be more than happy to discuss it in a discussion or Q&A session. So this is why there is this neutral smile for Java memory model and efficient compilation to hardware column. Now let's consider memory models in terms of DRF guarantee. Obviously, sequential consistency provide DRF guarantee because all behaviors in sequential consistency are sequentially consistent, not only for programs with node races. Java memory model also kind of provide DRF guarantee, and the main thing which allows Java memory model to have this DRF guarantee is that there are no out of thin air results there. So there is special mechanics, quite complicated one in Java memory model, which disallows out of thin air. But because of these mechanics, actually some compile optimizations are broken. So it's not very satisfying technique to be employed in other languages for disallowing out of thin air. And actually, C++ memory model has like the worst situation in this regard. Out of thin air, as I mentioned before, are allowed by the model, and this is bad. And actually, in this problem, out of thin air values is like main problem of weak memory research in the past years. So the problem is to develop a memory model which satisfy all desiderata. So we want to have compile optimization to be sound in our memory model. We want to have efficient compilation to weak CPU architectures like ARM or IBM Power. But also we want to have this DRF guarantee. We want to have this easy mode for developers to work with. So now let's take a look why this out of thin air problem arises in C++. So once again, this is the program with a problem of out of thin air. And actually the reason why C++ memory model allows to get A equals 1, B equals 1 result for this program is the mechanics which is used for defining semantics of programs. So let's take a look at these mechanics in more detail. So here we consider a program which is very close to the one we saw on the previous slide. But the only difference is that on the previous slide, from the problem in the previous slide, is that there is no control dependency in the left thread, so there is no if statement there. Okay, so in C++ memory model, semantics of the program is a set of execution graphs. So each behavior is explained by some execution graph. So here we have one of them. In execution graphs, vertices, which are usually called events, represent some memory accesses. So for example, here we have 3 events. The first of them is read x0. So it denotes that the first instruction in the left thread accessed location x and got value 0. Then it wrote 1 to y, this y1, and in the right thread there is only one access, reading access from location y, getting result 0. So in these execution graphs, there are not only vertices, obviously, but there are also edges. So here we have only one edge, which denoted PO, and PO stands for program order. So this is some total order which orders all events related to a specific thread. So this execution graph corresponds to outcome A equals 0, B equals 0. Since read accesses are related to read instructions in the program. There are more than that result which possible in C++ for this program. So, for example, result A equals 0, B equals 1 is also possible, and actually this is some sequentially consistent result, right? So we could get A equals 0, B equals 1 if we execute the left thread first and then execute the right one. So the execution graph has 4 events, one more comparing to the previous one. So now there is also a write access to location X in the right thread. Also, there is a new type of edge, this RF edge. So RF stands for reads from, and it connects write events with read events. So on the both ends, their events should access the same location and should write and read the same value. So this is the case here, as we see. So this is all behaviors allowed for this program in sequential consistency, but C++ memory model also allows to get result A equals 1, B equals 1. And the reason for that is because ARM architecture also allows to get this result. So if we execute this program in ARM, then ARM CPU could reorder instructions in the left thread. So this is how we could get result A equals 1, B equals 1. And the corresponding execution graph is presented on the right-hand side of the slide. C++ memory model, it's called denotational memory model or also axiomatic memory model. And the reason for that, because it also uses some set of axioms which to filter some executions which are bad. So one of the axiom could have a actually has a form of PO union some subset of RF to be acyclic, and most of the axioms have more or less the same shape. So some relation is either acyclic or irreflexive. So essentially we forbid some cycles in the graphs. So actually all of the graphs presented here satisfy C++ axioms. So all of them are allowed for this program. Okay, now let's back to our problematic program with control dependencies in both threads. So actually, if we allow this execution graph in C++ memory model, we should say that it's correct both for the first and the second programs, because we could get the same graph from them. Although you might notice that there is difference in these programs. As I mentioned a number of times already, there is control dependency in both threads in the second program. Although there is only one control dependency in the first program. So actually we could put these control edges in the graph, and this is actually what hardware memory models usually do. So they preserve dependencies and they have them in execution graphs. So the second execution graph might be forbidden if we have this control dependencies. So we would just add axiom saying that control union RF relations has to be acyclic. And yeah, obviously there is a cycle, so this is how we would forbid the second graph. However, it cannot be done for C++ memory model. And the reason for that is the following program. So it's very close to the second program, although it has else branch in the if statement. So actually, regardless of the value read by the first instruction in the left thread, 1 is written to y. So the corresponding graph could look like the one for the second problem with control dependencies. However, we know that the control dependency in the left thread is kind of fake, right? Because there is no real dependency, right? The write to y is done regardless of the value read by the first instruction. So if we want to allow compiler, let's say GCC, to optimize the left thread of the third program to by eliminating the if statement and just replacing it with write to y, then we'll get the first program, and for the first program we have to allow this result A equals 1, B equals 1. So if we want to allow this compiler optimization, we also need to allow the result for the third program. So we cannot use just we cannot just use dependencies to forbid some bad behaviors, or we need to have somehow a way to distinguish real dependencies from fake ones. And yeah, this is something which could be done, and actually, as I'll say later, there are memory models trying to do that, but it's actually a kind of hard problem, partly because there is no definition for real and fake dependencies, something which kind of subtle. Okay, so getting back to our table, there are solutions for this out of thin air problem, and in some sense the easiest one is RC11 memory model, which basically says that we'll forbid all PORF cycles in execution graph. So this RC11 memory model is essentially C++ memory model with some minor modifications related to some other tiny problems in C++ memory model, but also it forbids cycles, so it doesn't this PORF cycle, so it doesn't have out of thin air values in it. Although to obtain this, they have to compile to, let's say, ARM with some additional fences. This is why efficiency of compilation is not preserved fully as for C++ memory model, and also disallows some compiler optimizations. So now let's discuss how one could forbid these PORF cycles. So actually, to forbid PORF cycles, it's important to preserve order between reads and writes in the program. So essentially, we want this read followed by PO to a write edge to be respected in some sense in memory model. Now let's take a look why. So suppose we have some PORF cycle in execution graph of a program. So it has some number of PO and RF edges. Some of the RF edges also coincide with PO edges. Some of them are not in PO. So here we have an example of internal RF edge, and here we have some example of external RF edge. So as I mentioned earlier, PO, program order, is a total order on accesses to the same location, and as a total order, it's transitive. So we could reduce some edges in the diagram here. So now, essentially, we have a cycle only with PO and RF minus PO edges. So RF edges, they go from writes to reads. So in the left-hand side of the arrow, we always have a W, and then the right-hand side will always has R. So as we see, essentially it means that all of PO edges in the this cycle, they starts with the read and ends with the write. So since these external RF edges usually preserved by hardware, if we'll kind of preserve these read PO writes edges, then we'll forbid the cycle all over. And yeah, so now the question is, how do we make these RPOW edges to be respected? So first, we need to forbid reordering of reads followed by writes. Also, yeah, so this is to solve the problem with compiler. But also, if we compile to, let's say, ARM, where this order is not preserved by default, we need to insert something like a fence between every reader and write. And actually, the interesting bit is that forbidding these PORF cycles is much cheaper if it's done for language like C++ than for language like Java. And to explain why, we need to take a look at some specific property which specification of C++ has. And actually, it's undefined behavior. So usually, undefined behavior considered to be harmful for language, and if you manage to make a program programming language specification without undefined behavior, it's usually a win. However, here we'll see how existence of undefined behavior in specification of C++ allows to get more efficient compilation for PORF acyclic memory models. So let's take a look at the example program. So here we have two shared locations. So first it's a data. So this location we'll use to prepare some big data stored there. And then we have a flag, which is set 1 once the data is prepared. And then we transfer this, we use this flag to transfer data to the second thread. So for that, we have this busy wait cycle in the right thread. And if we say that both locations are just ints, then in Java, this program is fine. However, it might print 0. So it's not broken in terms of memory model. However, it's broken in terms of correctness, right? So we would expect that the only outcome possible for this program, I mean, we would like to it to be only 42, to be printed 42. However, in Java memory model, since some accesses could be reordered by compiler and then hardware, we could get the result. However, in C++ memory model, there is it would say that this program is bad in the sense that it has undefined behavior. So, for example, there is a data race on location F. So C++ memory model and C++ standard would give no semantics for this program. And there is a way to fix that. So actually, you could have data races on atomic locations. So you have to make this F flag to be atomic. But if you do just that, then you'll have a data race on data location. So to fix this, to fully fix this program, we also need to put some special annotations to the right of the flag F and to the read of the flag F. So the right is has this release notation there. So essentially, these release writes are compiled with some kind of fence, which if explained in simple terms, disallows reorderings of previous writes with it. So it would preserve order in the left thread. And also the read in the right thread, the acquire one also would prevent reordering of reading data before getting something non-zero for F. And yeah, so with these annotations, the program is correct, and now there are no data races. And the only outcome allowed in C++ for this program is printing 42. So if we compare Java memory model and C++ memory model, there are special class of locations in Java memory model, volatile ones and atomic in C++. They are kind of related in the sense that if you want to have some lock-free synchronization, like in the example, you need to use this type of locations. So if you have a data race on normal int location in Java memory model, it would say that, okay, the program is fine, but you'll have some weak guarantees. So, for example, in the first version of the program above, we would get a result 0, right, being printed. However, in C++, data races on int locations would mean undefined behavior for program. Also, Java memory model has this like normal int accesses. They are kind of related to relaxed accesses to atomic ints in C++, in the sense that you could have races on them, but you have weak guarantees. So actually, these accesses are subject to out of thin air. So in C++, as I said, there is nothing which prevents from having out of thin air. And in Java memory model, there is a special mechanics which disallows out of thin air for these accesses. Okay. So getting back to our table, we said that there is some special aspect of a language which interferes with memory model, and it's undefined behavior. So there is no undefined behavior, obviously, in sequential consistency in the sense of memory model. There is no undefined behavior in Java because Java tries to be safe language. And obviously, there is undefined behavior in C++. The same also allowed for RC11, which is essentially C++ memory model with some modifications. Okay, so I said that having undefined behavior in your specification allows for better fixes for the PORF cycles problem, right? If we want to forbid PORF cycles, if you have undefined behavior, it's less expensive in C++ than in Java. And the reason for that is that you have to forbid PORF cycles only for the read PO writes, which starts and ends with atomic accesses. Because if you have others involved in PORF cycles, then essentially you have undefined behavior, so you don't have to do anything about it. And usually there are less atomics in program than normal accesses, so it's less expensive to implement the strategy for C++ than for Java, where you would have to forbid all such reorderings. And actually there is a paper which studied this approach, so they also took LLVM and they tried to, and actually they succeeded in it to preserve program order between reads and writes. So as I mentioned earlier, to do that, there are two bits which have to be done. First, you need to restrict compile optimization, and actually interesting fact that in LLVM there are no optimizations which reorder reads with writes if they are on atomic locations. So nothing has to be done in this respect. Then the second bit for preserving this program order between reads and writes is related to hardware. So we want hardware not to reorder them in program. So if you do this for x86, then actually nothing has to be done because x86 by default preserve read to write order. Although if you want to do this for ARM architecture, you'll have to do something, and actually there are many ways to preserve this read to write order. So for example, the most straightforward one is to insert a fence. There are some special lightweight fences for essentially something like this. Although authors of the paper, they also tested some other approaches and like inserting a bogus conditional branch for each relaxed atomic read, and actually it showed better performance, so they decided that it's a better approach than inserting a fence. So and actually they get quite interesting results. So they get average slowdown of 0% for ARM v8 for a number of concurrent data structures from some benchmarks, and 6.3% slowdown at max. So obviously for x86 there is no performance penalty at all because you don't need to do anything. There is no modification, and for ARM the slowdown is kind of small and reasonable. Although still, even though this slowdown is kind of small, it might be that if you design a language like C++ and you want to have full control over performance, it might not be a solution for you. But on the other hand side, if you can trade a very tiny bit of your performance to get a much nicer semantics without PORF cycles, which are actually kind of hard, not only in terms of forbidding out of thin air values, but also for reasoning about programs. So maybe this is the way for you to go. But also, I need to point once again that this slowdown is that small only because it's done for language with undefined behavior on the data races for non-atomic accesses. Okay, so as we saw just now, preserving program order between reads and writes is good if it's done only for atomics. But is there anything to be done for languages with no undefined behavior if we want to forbid PORF cycles? So for that, let's take a look once again to this program, and we'll see that there is no actually a goal to forbid PORF cycles, right? But we want to forbid this result A equals 1, B equals 1 for the program, for the second program, not for the first one. So the difference again is these control dependencies. Okay, so one other approach would be to preserve all dependencies as done by hardware and not to distinguish fake from real ones. Then we would forbid result A equals 1, B equals 1, not only for second program, but for the third one, but maybe it's not that bad. And actually in the same paper, authors studied this. So they, again, took LLVM and modified a significant part of compile optimizations to preserve dependencies. So they modified 55 out of 46 optimization passes. Others they turned off, and they got average slowdown of 3.1% on ARM with a maximum slowdown of 17.6%. So yeah. Okay. So getting back to our picture, we see here that there is a solution for out of thin air problem, this RC11, although it pays some performance penalty for disallowing out of thin air. And actually there are other memory models which don't have any or much smaller penalty in terms of forbidding out of thin air values. So one of them is Promising Semantics, and it uses all of these three last memory models. They all use approach which is different from C++ memory model. So there are not just plain execution graphs. So for example, Promising Semantics is some operational semantics. So it's defined in terms of some operational machine, and this memory model allows a lot of compiler optimizations. It doesn't have to have undefined behavior for races, so it could be used for Java as well. There are no performance penalties because there are nothing which is allowed for hardware is forbidden for these semantics, although it's very different from memory models used used so far in industry. There is also weakest MO memory model. This memory model uses event structures to forbid out of thin air. So essentially, these event structures are some kind of mega graphs which incorporate many executions in the same graph, and this is how they are able to distinguish programs I showed before with the out of thin air values and to track real dependencies. The third approach, called modular relaxed dependencies, also use event structures, but for slightly different reasons. So they have some clever way to calculate some real dependencies and distinguish them from the fake ones using event structures. Although the problem is that their approach disallows some common compiler optimizations because they have to consider all possible values to be read while they calculate the dependencies. So yeah, but there are more than that. So there are some new memory models which try to get even more properties than discussed before. So for example, there is this ACAML memory model which trades performance to nicer properties. And let's take a look what the properties are. So we have this usual data race freedom guarantee, which says if in your program there are no data races, then you have only sequentially consistent behaviors for your program. But this guarantee is kind of global. So if you have some data arrays which might be irrelevant for the main part of the program, still you cannot use this guarantee. So for example, suppose you have a program like this. So here in the left thread, you have two writes to locations x and y, which essentially writes the same expression to both locations, this a plus 10. And in the right thread, we have x, we have a write to location x. So in this program, obviously, we have a data race between the first instructions in the threads. So we cannot guarantee SC semantics for it. However, one might notice that the write to x in the right thread, it doesn't directly affect the write to y, right? Because if we assume that both locations x and y are distinguished, then the write to y, it uses some value a and 10, and it has nothing to do with x. So, however, a compiler could do the following transformation. So it might see that there is some common sub-expression which could be written to some register t, and then could be reused twice. But also, after we use this register, compiler might decide that at some point it needs more registers for something, and it will just use the value stored to x to be written to y. So it's a normal transformation of the code, which is kind of usually could be done by many compilers. Although now, as we see, the write to x in the right thread affects write to location y. So a camel memory model forbids such transformations, and this is how it provides some local DRF guarantee, which says that if you have a data race on irrelevant locations, then it doesn't affect the, in this case, write to y. But to achieve that, a camel has to forbid some compiler optimizations and also have quite expensive compilation scheme to hardware. So last but not least, criteria which also could be used to rank memory models is simplicity of them. So actually, C++ memory model is quite straightforward. I hope everyone understands it. Java memory model actually has quite complicated mechanics for forbidding out of thin air values, so it's kind of complicated. C++ in this regard is easier because it doesn't have the mechanics. So RC11 is simpler than C++ memory model because it disallows some cycles, so it allows for more straightforward reasoning about programs. Memory models which solve out of thin air problem without performance penalty, they have some complicated mechanics for forbidding it, so they are quite kind of hard to understand but reasonable. And a camel memory model, it's also nice in terms of simplicity. So why this simplicity criteria is important? Because essentially it's important for software developers using language with memory model. So if it's extremely hard, then it's kind of hard to use it. But yeah, usually there is getaway for the situation with DRF guarantees. But if you have to write programs with if you need to write, let's say, log-free algorithms, then it's not the way for you to go. So yeah, you better have some simple semantics to be able to write. Okay, so to wrap up a bit, there are mainstream memory models like C, C++, and Java memory model, but all of them have some issues. So sequential consistency is not realistic, and it's kind of expensive to implement it in model languages. C++ memory model has this out-of-thin-air problem, and Java memory model has a problem with disallowing some compiler optimizations which are commonly used, and also it has kind of complicated mechanics for forbidding out-of-thin-air results. So if you're designing your own programming language or virtual machine and you want to pick some memory model, then you have to answer to some questions. So first of all, you need to decide if you are able to sacrifice some performance to get senior semantics, if you want to have very simple, very nice semantics, then you could go with sequential consistency, but that would mean that you cannot get the full performance from hardware. Then the question is if you can have undefined behavior, and maybe then you could simplify your semantics for the atomic part, which allows data races, but and have some performance trade-offs there, but to have nice performance for the rest of the language. And yeah, so for example, if you have a sequential program, probably you don't want it to be affected by your decisions, performance of sequential program. So yeah, if you have undefined behavior, you could do that. Yeah, then obviously the question is how complicated your memory model could be. So for example, if you want to have something in between sequential consistency and C11 in terms of performance, actually much closer to C++ performance, then you could have this RC11 memory model, which essentially have average zero slowdown on modern CPUs. Yeah, and then the question is how many guarantees you want to provide. If you want to have local DRF, then yeah, there is a way to go like a camel memory model does. So that's it for me. Thank you.
Anton, thank you for the talk. We don't have questions from the listeners, so I'll start with my own.
Okay.
Could you please stress up the meaning and the involvement of the control edges in the graph, because we are just following program order in your examples, so how is it adds to the cycle and protection?
Sorry, I didn't get that question.
Your control edges are following the program order, so how
Right.
is adds to resolution of cycles and
okay.
how?
Okay. Yeah. Okay. Thank you for the question. So the idea is that not all program order edges are respected in the modern hardware and consequently in the programming language memory models. So, for example, if you have right to read program order in x86, it's not respected because write could be buffered. So essentially, it could be observed as some reordering. Although if your program order is also a control order or data dependency or address dependency, then this thing is usually respected by hardware. So this order, if it's also respected by compiler, could be used for forbidding some behaviors.
Okay, thank you. Now it's more clear. My second question. And my second question, am I right that the currently applied C++ model is enough to correctly synchronize programs? So if you use decent places of atomic primitives, your program will be correct and it's okay. Or we just now have some problems.
I mean, the problem arises if you want to use these relaxed atomic accesses. If you have only them and you don't have synchronization, which is usually achieved by release and acquire accesses, then you might have problems. But yeah, if you put release and acquires in proper places or even SC accesses, right? So I didn't say that in the talk, but in C++, if you have atomic location, then once you access it, let's say you write to it, then you have like different modes you can use. So the weakest one is relaxed, then you have less guarantees, then you have release type, and then you have even stronger sequentially consistent accesses. So yeah, so essentially if you use these stronger access types, then you don't have this out-of-thin-air problem.
Okay, maybe you have some example of usual pattern would need to be used for some useful algorithm, but can be used now. Which of the famous algorithm is affected for now, which can be implemented without fixing the memory model efficiently?
I mean, I would say that there is no such algorithm, because you could always put just this release and acquire access in the places where you're supposed to get some synchronization. So yeah, on the top of my head, I don't have any like real example, but yeah. So this out-of-thin-air problem is actually arises there. You have these PRF cycles. So, and as I said, essentially it means that you have the PRF cycles for pure restricted to reads and writes, from reads to writes. So if you have some, it's also called like load buffering pattern. There you have some reads followed by writes, and the hardware allows buffer the loads, then you could get some problems.
Okay, we have actually a question about promising memory model, but I think we should transfer to discuss zone because it will be a large discussion, I think.
I could just say a couple of words about promising semantics. So yeah, essentially the idea there is to calculate dependencies to get like real dependencies. So and for that they have some nice mechanics which essentially has some certification which distinguish real dependencies from fake ones.
Okay, I think we could sum up and transfer to discussion zone.
Okay, yeah. So this was kind of interesting talk. However, there is a question in the chat about promising semantics.
Okay. I just answered.
Yeah, I mean the question from me, I'm not sure that I understand why somebody tries to get with other memory models if the promising semantics is like the good one. In your table, of course, it seems there's so many problems, others, but like it seems the promising is the solution to everything.
Okay, so actually there are some problems with promising semantics. So first of them is that currently in promising semantics there is no SC accesses. So I mentioned that atomic access in C++ they could be relaxed, release, acquire, or SC. So there are no SC accesses in promising semantics yet. So The other thing is that Promising Semantics, I mean, there are some directions for it to improve. So I actually took part in Promising Semantics 2.0. And the idea there is that most of the memory models, they allow some local optimizations, but they don't allow global optimization. So for example, if you like optimization, like taking a look at the whole program and getting that 0 is never written to some location, then you could remove some if statement and things like that. So, for example, this is what is missed in Promising Semantics 1.0, but is done for 2.0.
But is this like the crucial optimization? Because like the optimization that you said, like looking for the 0 if it's in there, is set like it doesn't look very promising in the sense of performance.
Not really. So, for example, if it's done in execution time, so if it's employed by just-in-time compiler, which has some information about values, or could just like use some optimized version of program until some other values arrives, then yeah, it could be used there, for example.
Oh, you mean in JIT? Okay, yeah, that explains a little bit. So can you probably tell more what is going to be in the next memory models? What their ideas are going to be there?
Yeah, I mean, essentially, ideas is to provide more guarantee with less performance penalty. Yeah, that's like the general way to go, and yeah, essentially try to forbid out of thin air.
Okay, yeah. So thank you very much for the talk, Anton, and Dmitry, thank you very much for your expertise.